In the previous session, we had seen some elementary applications of non-parametric and parametric bootstrap in R. Today, we would be seeing some more applications of bootstrap in context to finding out the estimates of the bias. In today's session, we would be following the codes which are given in the book Bootstrap Methods with Application in R. The second chapter of the book is what we would be doing today. So, we would be finding basically the bias estimates in context to a data which deals with the number of airline accidents in the United States. Further, we would take one example of the problems given in the same chapter and compute the mean and the standard error. While mean and standard error has some analytical components in it. So, that means that we basically know what is the form of the mean and the standard error, and we really do not have to employ Bootstrap per se to find out the approximate confidence intervals. It really is not so simple in context to the medians. So, for the same data, we would also be estimating the medians and finding out what is the confidence interval in context to the median when we apply the bootstrap technique. So, here we would be talking about some more applications of bootstrap in R, and the reference is Bootstrap Methods with Application to R by Michael R. Charnick and Robert A. Labud. So, we would be using some of the worked out examples of this book in this video, in this session, as well as in a couple of subsequent sessions. Now, we start with adjusting bias using the bootstrap. Now, how do we do that? So, just a small recap. Now, bias for any estimated theta hat. So, theta hat is an estimator of theta is B, which is expectation of theta hat minus theta. Now, let us take an example. So, let us take the example of univariate random normal variable. The MLE of sigma square is the sample variance with divisor n, that is I runs from 1 to n x I minus x bar square by n, where x bar is the sample mean. Now, we all know that here the bias is minus sigma square by n. The bootstrap estimate of bias B is B star, and not to be confused with the number of repetitions, but here B star means the bootstrap estimates of the bias. So, B star is expectation of theta star minus theta hat, and in our case theta hat is S n. So, that is expectation of theta star minus S n. What is theta star? Now, theta star is summation I runs from 1 to n x I star minus x bar square by n, where x I star is the ith replicate of a bootstrap sample, and we repeat this process say capital N times. Then the Monte Carlo approximation to B star, that is the expectation, is replaced by the average, which is summation Bj star by n, where Bj star is the estimate of the bias obtained from the jth bootstrap sample. That is Bj star is theta j star minus theta hat, theta j star being the sample variance of the jth bootstrap sample. Now, again we set this, use the command set.seed for reproducibility. So, let's work this out in R, and we start with say n equal to 25 samples. Take a random normal sample of size n from normal 0 1, that is a standard normal variable. Then variance of x is variance of x, but R computes the divisor to be n minus 1 by default. So, to get the uncorrected variance, we multiply variance of x into n minus 1 by n. That means, var x is 1 by n summation I runs from 1 to 25 xi minus x bar whole square. Now, the sample variance and bias relative to true value of 1 can be calculated out. So, how do we calculate it out? So, the sample variance is var x and the bias relative to the true value 1, because we know that the data comes from normal 0 1 is var x minus 1, and also the expected bias from theory is minus sigma by root n. So, that is minus 1 by square root of n, and if we do that we get the value to be 0.866 minus 0.133 and minus 0.2. Now, let us perform a bootstrap sample to adjust the bias. So, we set capital B equal to 5000 and this capital B works the way we have defined capital N in the theory in the previous slide. Then bootstrap variance x, that is B var x, we initialize it to null. We could have initialized it to say rep Na comma capital B also. Whatever is so necessary we can do, but we just initialize a vector which would contain the resample variances, and then for y in 1 to b, that is for each of the resamples, we first draw a sample from x. So, basically we are doing a non-parametric bootstrap here. We draw a sample from x with replace equal to true option and then calculate the bootstrap variance, and since we are using r which has a divisor n minus 1. So, we adjust it by n minus 1 by n, the multiplying factor, and thus we get the uncorrected resample or the bootstrap variance. Then theta star is mean of the bootstrap variance of x, B var x. So, that is, so we get an estimate of the variance. Then what is the estimate of the bias? So, theta star comes out to be 0.82884859 and the bias comes out to be theta star minus var x, that is minus 0.03773855. Now, if we see the bias has reduced in the bootstrap variance context. We can also use the jackknife. Now, using the jackknife is easy because obviously, I mean there is a package boot which does all this. There is also a package called Bootstrap that needs to be loaded. So, the jackknife can be performed pretty easily by the jackknife function in the Bootstrap package. So, require Bootstrap and then define theta, which is the parameter of interest that we are going to estimate, which is function x var x into n minus 1 by n, and that is the uncorrected variance, and then just simply call jackknife x theta, where x is the sample, and then store it in an object called jack. So, if we see what jack contains, jack is a list which contains jack.ac, that is the standard error, jack.bias, that is the bias, jack.values and call. So, if we take the mean of all the jack dot values, we would get the jackknife variance, and that comes exactly equal to the sample variance. As an exercise, we would be doing the first problem of the second chapter of Bootstrap methods with application to R. As an extension of our application of Bootstrap, here we would also be demonstrating the first problem given in chapter 2 of the Bootstrap methods with application to R book. So, the problem there gives a data about airline accidents, and according to the problem it says that according to the US National Transportation Safety Board, the number of airline accidents by year from 1983 to 2006, where then there are the numbers. For the sample data, compute the mean and its standard error and the median, compute the same bootstrap estimates. So, the problem is that we are given a set of numbers, and from that we have to find the mean, the standard error and the median. Also, we have to repeat the same estimates, but using bootstrap technique. Now, this should be pretty easy now. given that we have done a couple of exercises in R. So, what we do is again set dot seed for reproducibility, and one can have a different seed numbers. Define the vector x, which is the number of accidents per year. N is length x, b is 1000. So, we set b to be 1000. Then define 4 vectors, which is x mean, x median, x standard error, AC mean, and x standard error median. And then what do we do? For I runs from 1 to b, that is we repeat the same process b times, and by now when we say b times, what we have to do is we have to sample, or we have to take b bootstrap samples using the sample command in R. So, sample x n replace equal to true, so that it produces samples with replacement, and then for each of the bootstrap sample we find the x mean and the x median and see what exactly are the values. So, for the original data, if we just compute mean x and SDX by square root of n, that is SD by root n, the standard error, we get the values to be 33.791667 and 2.462751. We can repeat the same thing, but this time what we have to do is we just, for the bootstrap context, we just find the mean of x mean and ST of x mean, not the standard error. So, here one needs to be a bit careful in context to a bootstrap, because we are dealing with the bootstrap means. The standard error of the standard deviation of the bootstrap means is nothing but the standard error. So, the value comes out to be 33.690417 and 2.472755. So, the median is 30.5, and it's really difficult to get a standard error of the median at one shot from this, but using the bootstrap we can always get what is the standard error of the median. So, here if we use mean of x mid, it comes out to be 31.421500 with and ST of x mid. So, that gives the standard error of the medians, and which is 3.880741. So, we can use this and compute a confidence interval, approximate confidence interval for the medians also, and just if we take median of the bootstrap medians, that value comes out to be 30.5, which is same as median of the original data. In today's session, we have seen some applications of the bootstrap technique in R. We have used bootstrap to find out an estimate of a bias in context to the mean for a small data set. We have also done a exercise in R, where we were given our data and we obtained the mean, the median, as well as the standard errors of both the estimates using the bootstrap technique. Further, we have obtained the confidence interval using the bootstrap technique. In the next session, we would deal much more with the confidence intervals, because we know that in a bootstrap their confidence intervals can be calculated using multiple ways. So, in the next session we would be seeing how to calculate 3 types of confidence intervals: the percentile confidence interval, the percentile t confidence interval, and the bias corrected confidence interval in context to bootstrap.